All right, let's dig into our kinematics model. So, as a reminder, what we're trying to do here is we're basically trying to come up with a relationship between inputs and outputs. So our outputs are going to be dependent on some values for our inputs. So what are our outputs? Well, in previous lectures, we defined the outputs as our rates of change of essentially the pose, but I'll use the terminology we used before, which was of our state. And we used the symbol Q for the state, which happens to be very similar to the pose we talked about before. So Q dot is our values for x dot, y dot, and theta dot. And those should all be defined with respect to the global coordinate frame. We don't really care what they are with respect to the robot's coordinate frame because we know it's always defined to be at 0, 0. On the inputs side, we have the current state. Which is the values of x, y, and theta. So the pose. I should mention those are not always the same thing. You're not always going to have your pose be the same as your state. Sometimes your state will include things like your velocity or acceleration, depending on what kind of control algorithms you're trying to implement. So those can be part of state, but they wouldn't be part of pose. You wouldn't have velocity as part of your pose. The pose is really just a static quantity. Other inputs to our kinematics model would be physical characteristics. And our final input are the actual inputs to the motors themselves. So how fast are we turning the motors? So putting this all together, we'll have that our output, so how quickly our robot is moving in the global coordinate frame, is equal to a transformation based on our current state. In this case, the only thing that really matters is the value for theta. So x dot depends on the cosine of theta and the sine of theta. And specifically in reference to the speed of the two wheels. So cosine of theta for the speed of the right wheel, and then sine of theta for the left wheel. And to turn the rotation of the wheels into a linear velocity at the point of each wheel, we need to multiply by the radius of each wheel. And then we divide by 2 because it's the average velocity of each point of the wheel. And that's probably worth showing in a diagram. So it's useful to think about the velocity at this point and the velocity at this point. And that's really what these multiplications are doing. Cosine times r over 2 times phi right, and negative sine times phi left times r over 2. That gives us the velocities at these 2 points, which we can then use to figure out what's the velocity in the global coordinate frame. And then filling in the rest of this transformation matrix. We have our final kinematics model. And essentially what we want to do is figure out where is the robot as we rotate the wheels. So we set the PWM duty cycles, and that results in rotating the 2 wheels. And we want to know what happens to the values for x, y, and theta. So how much do we rotate in our global coordinate frame, and how far do we move or translate in the global coordinate frame's x and y axes? So the second part of this is called forward kinematics. How do we actually use this model from the previous slide to track our position over time? And so one final label I'll give here is, don't forget this vector on the left-hand side is our state, q dot. And what we want to know is, what is our state at any given time? Well, q0, we're almost always going to define as being at location 0 on the y-axis, and then a rotation of 0. What's more interesting is, what is our position, what is our pose rather, what is our state at time 1 or time 2 or any time t? Well, if you've taken a calculus class recently, you probably have something like this in mind. Q at time t is equal to the integral from time 0 to time t of our equation from the previous slide, this one here. And let me label these other matrices just to make our lives a little bit easier. We'll call this T for the transformation matrix, and that's going to take us to G from R. I'll call our physical characteristics matrix P for physical characteristics, and then traditionally we'll call the control values U, and that's going to be a vector, so I'll do it in lowercase cursive. So we have T, P, and U. And if we wanted to, there are ways to move p outside the integral since it's a constant with respect to the integral, but we'll leave it there for now. One thing that complicates this, actually computing this integral, is that we're doing this on our microcontroller. And our microcontroller is not operating, or at least the software on it, is not operating in a continuous space. So instead we're going to look at a discrete version of this. And traditionally we'll use k to remind ourselves that we're looking at a discrete version of this. And we'll have our same quantities, essentially. And I have a bad habit of turning my u's into mu's. And we're going to sum from 0 to time k. You all having familiarity with imperative style programming, or I guess I would say non-functional programming, you're probably used to seeing this in a slightly different form, where we're using mutation. So we'll write that form here because it's closer to how you will do this in code. We'll say where you end up at the next time step is a function of where you are at now. So if I were to quickly draw a diagram here, and the robot is currently right here facing this direction, you would say that its current location here is Q at time K. And we're more interested in finding Q at K plus 1. So where will that be? Well, since I drew the heading in this direction, it's probably something like in that location there. But it also depends on the angular rate of the robot itself. So let's say it ends up here, and that's Q at K plus 1. How do we compute that we've moved from this location up to this location at Q plus 1? Well, that depends on our current angular velocity and our linear velocity, which is precisely given by Q dot. Which is exactly this equation here from the previous slide. However, we're not going to put a dot here. Instead, since we switched from a continuous time to a discrete time equation, we should do the same thing here. So these will be roughly approximate to each other, but we'll call this now delta Q at time K. The K there is just indicating that we could have a different linear velocity at different time steps. The last thing that matters is it matters how long we were traveling at this angular and linear rate. If we were doing it for 1 second, maybe we jump from here to here. If it was for half a second, we want to jump half as far. If it was 2 seconds, then we would jump twice as far. So the amount of time that we're traveling at this rate also matters. And I'm now realizing I was missing my dt up here, which is a nice reminder that we would have a delta time in the discrete version of the equation. And I should wrap up by denoting that in the diagram above, I denoted the jump by a red line here, the position we landed at by green, and the initial position by pink. That's how you would read that diagram. So in your code, you would have something like Q plus equals, or if you broke Q out instead of it being some sort of object in C++, you could say X plus equals, Y plus equals, and theta plus equals. And that'll be a nice place to drop off for this video. And in the next one, we'll put all this together and start being able to direct our robot to a specific goal pose.